So in this problem, we're tasked with finding the volume of a solid of revolution given the following. We're given the function f of x, which is the natural logarithm of x, the function g of x, which is 0, and this is just the x-axis, and then our axis of revolution is x equals 0, which is just the y-axis. And we're also given a domain for x, in that x is a member between 1 and pi inclusive. And so, the first step in solving any solid revolution problem is to determine what method you'll be using. And we can do that by looking at the variables that our functions are expressed in. If we do that, we look at f of x is expressed in x, g of x is expressed in x, and our axis of revolution is x equals some value. That value is 0. Because all of these functions are expressed in terms of the same variable, we can use the shell method. If these two had been the same variable, but this had been different, say f of x, g of x, and our axis of revolution was y equals some value, we could no longer use the shell method without modifying our functions. We'd have to use the disk method in that case. But because they're all equal, we can use the shell method. And whatever method you'll be using, the first step after this is the same. And that is to find whether or not we need to modify this domain that they've given us. And we do that by finding where our functions here equal one another. And they equal one another only at one point, and that point is x equals 1. But if we look, that point is already on the cusp of our domain. We don't need to make any adjustments to this. If it had been somewhere between 1 and pi, we would have had to split this domain up and done more work. But because it's not, we can just restate the original domain given here. And now that we have this, and we know that our domain is correct, what we need to do now is we need to determine which of these two functions is greater given this domain. And we can do this one of two ways. The first way would be to use the graph of the two functions, but that's cheating, I feel. The second way is to look at it numerically, which is my preferred option pretty much any time it is an option. And we can choose some value c that is within this interval and not including 1 nor including pi, and I accidentally wrote the brackets there when I was writing this, so those are parentheses, just to be clear. And c just needs to be some value between there. It doesn't matter what it is. So I chose c equals 2 because 2 is a nice pretty number. And what we're going to do with this, we're going to put it in both of our functions to evaluate to see which one is greater for this value c and therefore greater for this entire interval. So we have f of c equals the natural logarithm of 2, I just plugged it in, and g of c equals 0 because g of any value is going to equal 0. And we don't need to know what the natural log of 2 is because it's greater than 0 regardless of what it is. And that's the only reason we ever did this, was to determine which one was greater. The actual value doesn't matter. And so we can say f of c is greater than g of c. This is true. But we can use this to broaden this statement just a little bit because we said that they only ever cross at x equals 1. Because they only ever cross at x equals 1, these two functions are going to relate to each other the same for every value greater than 1 and every value less than 1. So because 2 is greater than 1, and f of 2 is greater than g of 2, f of x is going to be greater than g of x for any value greater than 1. And specifically for what we care about, it's greater between 1 and pi. Notice that our original domain includes 1 and pi, but down here we do not include 1 and pi in our domain. And that is because for the shell method to work, we need to determine which of these is greater over the domain. If I had put 1 is less than or equal to x, then this statement would no longer be relevant because I need f of x to be greater than g of x, not greater than or equal to. And so we drop the equal to part right here and can say that f of x is greater than g of x is greater than our axis of revolution value, which is 0, just to remind you, on the interval 1 is less than x is less than pi. Continuing where we left off. Now that we know that f of x is greater than g of x on this interval, we can construct the formula for the shell method. So let's do that. The formula for the shell method is a volume, which is what we're looking for, equals 2 pi times a definite integral of our greater function f of x minus our lesser function g of x times x. And we multiply by x because and only because our axis of revolution x equals 0. If x had equaled any other value here besides 0, then we would not be multiplying by x, we'd be multiplying by that value minus x. But when it's 0, it's special, and you multiply by just x. And so I'm going to plug in our f of x, which is natural log of x, and our g of x, which is 0. And this 0 is just a formality because it's going to simplify away right here, and we'll be left with our volume equaling 2 pi times a definite integral from 1 to pi of x natural log x dx. And the way that we solve this is with integration by parts. There. And to integrate by parts, we first need to assign some part of this function to be our u value and some part to be our v prime value. And if we look at the acronym LIATE, standing for logarithm, inverse trigonometry, algebra, trigonometry, exponents, this is a hierarchy of u values. Because we have the natural log of x, that's at the very top of the hierarchy, and so that's going to be what we use as our u value. And everything else is going to be our v prime. So our x here is going to be our v prime, because that's all that's left after we take out this natural logarithm. Now, from here we differentiate ln of x, which is 1 over x, and then I break this up into 2 steps because I don't know why. It's just habit. So u prime is 1 over x, and du is 1 over x times dx. And then over here with our v, which is just x, we integrate that to get v prime is x, and v is x squared over 2. Now then, we can go on to actually solving this equation. So, a moment ago, we found our u and v values to use in integration by parts. And this is just a generic integration by parts formula. And so the integral we had a moment ago turns into this, with our u and v defined, and then evaluated at pi and 1. And so if I plug in the u and v values we had u equals ln of x and v equals x squared over 2. So we combine those into this. And then we subtract 1/2, which was our x squared over 2, that's the 1/2 from there, pulled it out, times the integral of x squared times du. And our du was 1 over x dx. And so this becomes our new integral, and this is much easier to solve. And then we evaluate this at pi and 1. So the first thing I'm going to do is I'm going to combine my x squared and my inverse x to get 1x. And that's all I did in that step. Pretty self-explanatory. Next, I'm going to factor out a 1/2 from both of these, because they both have them. I'm going to factor them out of this expression because it's a constant, and I'm going to have 2 pi over 2, which cancels down to simply pi. So I'm left with x squared ln x minus the integral of x dx, evaluated at 1 and pi. And this is becoming much, much, much simpler. So what we do here is we integrate, and that integration is very simple. It's just x squared over 2. So we have this evaluated at pi and 0, and we could go ahead and plug in our values. If you had a calculator, you can plug them directly into the calculator. But since we're doing this by hand and doing it algebraically, I want to show every step, and I think the simplest way to solve this would be to factor out another 1/2 from here. And so I factor out that 1/2 to get pi over 2. And because I factored that out from both of these, I multiply this one by 2, which just gives me x squared, and this one by 2, which gives me 2x squared ln x. So now I can factor out an x squared, not out of the entire set of parentheses, because it does need to be evaluated, but I can factor out of here so that I have 2 natural logs of x minus 1. And from here, this is very simple, and I can plug in values very easily. And so when I plug in my values to find my volume, I get this, my pi over 2, which is a constant, so it's staying out front, times pi squared times 2 ln pi minus 1. And then I subtract this evaluated 1, which is 1 squared times 2 ln 1 minus 1. And when I simplify, ln of 1 is 0. So this entire, this part of this expression goes away. 1 squared is 1. So I'm left with over here, I'm left with 1 squared times negative 1. But that's being subtracted. So that negative 1 is going to become a positive 1. And over here, all I did was I distributed that pi squared. So I'm left with 2 pi squared ln pi minus pi squared minus -1 or plus 1. And then we have this pi over 2, which has been hanging out front, and it will continue to hang out front because now we are finished. Congratulations.